Okay, so now we're going to talk about ways in which we can represent the pose of the robot and poses of different things in the world that's observed by the object. And if I were you, it would sound super boring, but in reality it's not. So it has a bunch of interesting mathematical properties that are pretty damn interesting. And also it's just something that's really important in practice. So if I had to guess, like 80% of the problems that I have seen so far in VSLAM was just coordinate systems. So it was trying to compare or like optimize against or process things that were just in different coordinate systems. So just something to keep in mind. Just something to be really careful about when implementing the system. All right, so let's jump into it. All right, so here we have the screen. Yeah, let me erase this real quick. So actually there's a couple of ways to represent. So wait. So first of all, we're going to work on 3D pose. Come on. 3D pose. And 3D pose, it has rotation component and it has position component, right? So let's say that we have like a type of, so here's like our coordinate system, right? And here's like our tiny robot. Now it has legs and it's looking this direction, right? So not only it has some coordinates, the position where it's at, but also it has like its heading. So it could also be standing on its head, and that would be a whole different pose. So it would be seeing just completely different stuff. So pose has the translation component and it has the rotation component. And those two together is pose. And pose is always measured with respect to some coordinate frame. Coordinate frame. So what I mean by this is like there needs to be some kind of 0.000 with respect to which we are measuring, and then like with respect to this which we are measuring the pose of the robot. If our coordinate system was starting here, for example, right, that would be a completely different pose, right? The numerical value of the pose would be completely different. So that's a pretty important point. All right, so there's a couple of ways to do this, to express the pose and translation and rotation, and I'm going to focus on one specific one, but I'm just going to also briefly mention the other ones just for your background. So the main one that we're going to focus on, let me summarize it first, and then we'll like backtrack and slowly reintroduce it and just talk through a bunch of like examples and so on, and hopefully also code something up, because that's really important. But anyway, starting from the summary, right? So we're going to represent each pose, so both translation and rotation, in a 4x4 matrix. And so this way to represent the pose is called either SE3 or sometimes it's called homogeneous coordinates. Yeah, so how it works is it has this 4x4 matrix, it has compartments sort of, so it has like 3x3 rotation matrix, and then it has 3×1 translation vector t, it has a tiny little 1 over here and a bunch of zeros. So, by the way, just for clarity, sometimes I will write zeros as dots, and this is purely to help my handwriting. But when you see a dot, you should think 0 inside a matrix. So let's take an example. Matrix may be something like 1 0 0 0 1. Actually, I don't really need those. And maybe 0.7 and then 0.3 and then minus 0.2. So, and then 0 0 0. So this means it's like unit, so there's no rotation, and this means, so this is like x axis, y axis, and z axis. So you have, if I have like a coordinate system which I label like this, then I will have, okay, 0 7 along that, so maybe it's here, and then 0.3 around along the y-axis somewhere like here, and then minus 0.2, so there's like something, so right here there's like a point over here. This is my point that's represented by this pose t, and then what I will write is like that's the position of the point. So sometimes I call like point pose a transform. So it's a transform that takes me from the beginning of this coordinate system to where this point is. So I write this, and then really important thing, right, that I have learned from a good friend of mine. So I always write with respect to which coordinate frame the pose is, right? So if I just zoom in into this notation, right? So I have a t, so it's a pose of a point with respect to coordinate frame. I always write down with respect to what coordinate frame given pose is. Right, so that's like the high level idea of how we can write out those poses, and then now let's zoom into some details of this representation. So first of all, let's look at the rotation matrices, right? So let's take a step back actually and look at two-dimensional rotation matrices, right? So if I have in two-dimensional space, if I have a vector, let's say it's a vector like 2 1 or something, so v is equal to 2 1. Yeah, I should write it in a proper way actually. Let me write it like this. And then I may have like a rotation matrix, and I mean you could just read it in Wikipedia, but like I remember it like C minus S C, right? So this is short for cosinus, so it's like cosinus alpha, sinus alpha, cosinus alpha, and then minus, important thing, minus sinus alpha, right? And my rotated vector v prime is r times v. So just hold along, you know, like let's call this vector ab actually, instead of like 2 1. It's like a times cosinus alpha minus sinus b sinus alpha. So this is my first coordinate of the output vector, and then I would have alpha sinus alpha minus plus b cosinus alpha. So this is how this basic thing works, right? And like, yeah, I could just choose. So there's basically only like one possible rotation, right? Like we could only rotate the whole coordinate system to the left or to the right? So at least when we are rotating around the beginning of the coordinate system, if we're rotating around this 0, 0 point, so we can only rotate left or right. So we can only have, so there's sort of only 1 degree of freedom. We could be rotating by like positive alpha or negative alpha, but that's it. There's only so much we can do. There's no like 2 ways to rotate a point, and this is to rotate the coordinate system. And this is different compared to the 3D case, right? So in 3D case, there's like a bunch of different rotations. So we could be rotating around this axis, around this axis, around this axis, and whatnot. So the situation is a lot more complicated. But anyway, coming back to this is kind of like a simple situation, and it can be all written out this way, right? And then we see this interesting thing, right? That like the alpha is 1-dimensional, right? So it's like a real number. And the rotation matrix that represents this rotation is 4-dimensional. So it is 2 by 2. So 2 by 2 is 4. So it's just like a different representation, and there's like a clear mapping between those, right? Well, it's not really R, right? So it like wraps at some point, but there's a clear mapping between those. So we can efficiently, we can encode all the information about the rotation just in this one number. And then I'm not going to prove this, but we could prove that this matrix R, it has a bunch of properties, right? So first property is that for each alpha, determinant of R is 1. And then we could also prove that the inverse of R is RT. And this is actually a nice exercise. I leave it as an exercise to the interested reader. It's a relatively easy thing to prove. And then we will say that each, so sort of the, so if we denote the rotation matrix that corresponds to the rotation by alpha by R of alpha, we could define a group of all rotation matrices of 2-dimensional space as SO2. So one way to define it is it's a group of all possible rotations. So here's like one way to define it, and this is actually equivalent to saying this is group of all matrices such that 1 and 2 are true. So those are equivalent. So there's like this interesting correspondence between those two things. And bear with me, I mentioned it for a reason. So maybe I should go into this reason right now before I even go to this three-dimensional case. So often when we do robotics, we want to do optimization. So we want to say, okay, so here's like our goal function. Maybe this is like yeah, we need to like optimize trajectory of the robot, or maybe we want to minimize some kind of loss, something like this. And we have some kind of abstract, maybe multi-dimensional function x, right? And then let's say we're here, and then we can just measure the derivative of this function. And then we want to move the x the tiniest bit, right? Let's say dx, such that in a direction such that the df is most negative, right? Such that the f goes down. And then if we are doing this over just normal real space, it's pretty nice, right? Like if we just look at the just even the definition of this, right? So like what we really mean is like this fx plus epsilon, right, is equal to f of x plus epsilon times f prime of x plus some error, and then this error is negligible. So basically this is like a Taylor theorem, right? And then and all of this is basically just like a definition of the derivative, right? So it's like I could just rearrange terms and just say this pretty much. So right, and yeah, I just like plus this plus error, and then error is negligible, right, as epsilon goes to 0. So this is sort of the definition of derivative, right? And then you will notice that you need two operations in order for this definition to work. So you need to have addition, and then you need to have multiplication. So you need to have those two operations for all of it to work. And then so let's say that right now, right, that we have that maybe we need to optimize some function f, and now this f is a function of rotation. And then what you will notice is that it's pretty hard to choose a definition of this rotation in such a way that this formula makes mathematical sense. And this might sound a little bit abstract right now, but like let me give you a concrete problem that we have with our definition of the rotation, and that comes from SO2, and how this definition of derivative and like function optimization, gradient-based function optimization won't work. So if I have basically I can have a rotation, and then like let's say R represented by matrix. So let's say I have like R alpha, right? And maybe so again like so maybe I had like alpha of 30 degrees, right? And then I would substitute, so cosinus minus sinus, sinus cosinus, right? I would substitute those into the cosinus formulas, and then like that would be my R of alpha, right? So let's say I do this, right? And then this matrix, it has all these nice properties. So it has like determinant is 1, and then it's orthogonal, so this is true, right? And then I take let's say another rotation, right? And this rotation is, so I say like, okay, if I move my coordinate system a little bit to the left, so maybe I have, for example, like a ball, right? And then I have another ball, and then I'm asking, okay, what's the rotation that aligns those balls? So I don't know, like roughly that's like 30 degrees or something, right? And like I could totally ask a mathematical question like this. So then like, what's the epsilon that makes my rotation? So let's say I have like epsilon, and then like tiny rotation beta, right? So maybe beta is like 0.01 degree or something. So I try to move the whole coordinate system, rotate it a tiny bit, right? But like the problem is, if I just look just purely based on representations of those rotations, right? So maybe like my rotation was something like 0.7, then minus 0.7, and then like 0.7, and then again 0.7, right? Something like this. Crap, wait, this is like even, let me just figure out what's the right rotation. Let me just give a concrete numbers for this. Let's take this. Okay, from like how do I do like numpy 2D rotation matrix. Okay, yeah. Let me do like theta equals np import numpy s np. Theta is np dec to rats 0.45. Let's do this. Okay, what's this? Ha! I was right. Okay, we just wasted a bunch of time. Anyway, maybe I just cut it out. Right, so anyway, so coming back to this, right, so our starting rotation was something like this, right, and then we take this, and because this beta is really small, right, then it's like something like 0.99, 0.1, and then 0.01, and then 0.99. If I add those together, the properties, and so I add those together, right, and then I call this maybe like R new. The R new actually doesn't have the properties 1 and 2. So just naive application of the formula for the derivative and derivative based optimization doesn't work. And there's even easier way to see it, right? So like if I just take identity, which is a valid rotation matrix, and I add another, like even epsilon times another identity rotation, which is basically like I would, in terms of adding rotations, I would suspect that this does nothing because it's like identity plus identity. It should be identity. I do not get identity. I get something else. I get something that completely doesn't belong to this group. And this turns out to be a major problem. And it feels like the rotation should be something that's natural and regular, but it's surprisingly hard to come up with a representation that's nice and regular. And for this 2D case, we have the R, just normal rotation, expressed as one number. And this is enough. This is enough to express the optimization, but it's definitely not the case in multidimensional case. And there's a whole branch of mathematics called Lie theory that studies what's really going on there. So yeah, that was like a Lie theory and toughness of choosing the right representation. Side note. Now we can go back to more like robotics based stuff. So yeah, so now we're going to look at rotations in 3D. So 3D rotations. So for 3D rotations, we can have rotations around this axis, and rotation around this axis, and rotation around this axis. And there's like a kind of like complicated formula, right? So 3D rotation matrix wiki. I will show you how I reason about it, how I remember it. Right. Yeah. So basically, here's like a generic 3D rotation, right? You can see that the formula is kind of complicated, right? So we can have rotation around one axis and second axis and third axis, right? And then it ends up being like this 3D 3x3 rotation matrix. Then let's see. So one easy trick that I use, right? So like if I have So this is my starting rotation matrix, right? It's an identity rotation. And then I want to have a rotation that is rotation around X. Then I remember that it needs to preserve the first coordinate. It preserves the x-axis, and then so it doesn't do anything on those, so those are kind of banned. They have to, all of those have to stay the same, right? Like this and this. So I'm only allowed to modify this one over here, right? So it's the same C minus S, CS. So cosinus minus sinus, cosinus, sorry, sinus, cosinus story. And then same thing really if I want to have something that preserves the y-axis. So I write out my rotation matrix, this basic rotation, and then I know it has to preserve those, so you have like C minus S, S, C, right? So I mean that's like pretty basic stuff, but that's how I remember it usually. And then those 3D rotations, right? They also have those two properties. So first property is the specialty, that's how it's called, like it's the S in SO3, special orthogonal, right? So they have the specialty and they have also orthogonality, which means this, that the inverse is the same as transpose. Yeah. And then one thing I should mention, but I will just mention it real quick, is that there's so maybe some of you are familiar with the imaginary numbers. So there's sort of like, okay, here can be the real part, here's like the imaginary part, and then you could have cosinus plus I. So if I take like a unit imaginary number x, it will be cosinus phi plus I sinus phi, right? So it's sort of like saying, you know, it's this much of the first coordinate and then this much of the second coordinate, right? And then you could actually extend this idea to have 3 imaginary axes. And it sounds pretty crazy, but so in I, right, you had this idea of I squared being minus 1, and in this new word you could have an idea of ij being equal to k, and then so on and so forth, and then I squared still being minus 1 and j squared being equals to minus 1, and so on and so forth, right? And then it's kind of hard to see right now, but like you could now express arbitrary rotation of the 3-dimensional space as a sort of combination of the vectors I, j, k. So it's like sort of like alpha rotation around the x-axis plus, well, not really, this is not completely, not around the first axis, and then beta times j, and then let's call it gamma times k, right? And then you could have scale those such that they are equal to 1, right? And this is like a nice representation of this is pretty nice representation of the rotation, because instead of 9 numbers as our rotation matrix does, it only uses 4 numbers. So there's like also real parts, right? So that's way way more convenient, and also just like it's also probably a little bit hard to see right now, but like if I have in practice, right, if I have a lot of rotational matrices, right, so I have like I'm expressing a chain of poses, or maybe I have been accumulating some poses for quite some times, it can happen only inside the computer that multiplication of many rotational matrices due to accumulation of float errors, so the determinant of this matrix, right, so that of this, let's call it some kind of like R sum or something, that it will be just numerically not equal to 1, and then making it again numerically equal to 1 is a little bit harder and a little bit less natural than making those numbers sum up to 1 again. So that's convenient, and that's a nice way to control for those. Alright, so I feel I'm missing something, right? I'm not sure if I explained everything I had from these rotations, but let me just leave it at that for now. And then let's look at, right, so as we talked in the beginning, right, we have this like 4x4 matrix, and there's like a rotation and so on. And now we can see, let me mention two things. So if we have, so this 4x4, so here's like rotation, and here's translation 1, yeah, and let's say this is T of object A in reference frame of object B. And then we have two really nice properties of this system. So one system is that if we want to know what's the position of object A in reference frame of object C, we have the following property. They cancel out, sort of. So we could, if we know the position of object B in reference frame C, and vice versa, if we know the position of object A in reference frame of object B, then we have all we need to learn the position of object A in the reference frame of object C. So that's really one very nice and important property. And the second thing, which is very cool, is that we can invert those. So the following is true. If we know the pose of object A in reference frame of object B, we also know that we can invert this matrix, and then we know what's the position of object B in reference frame of object A, right? And then what this means in practice, or like let's see how we can use this in practice, is like if we have a word frame, right? So let's say this is a word frame which sort of begins in the beginning of the word, I don't know, like Greenwich or something, right? And then we have a robot over here, right? Robot. And then we have object over here. So let's say like a landmark star. If we know, so we know one, the position of the robot in the word frame, and we know as well the position of the star in the word frame, we can compute what is the position of the star in the robot frame. And the way to do this is to do the following. We want this to be on the left, so we invert it. So we do robot, and then we put a word here, so this is just this but minus inverted, so that's 1, and then we literally multiply it with position of the word frame in the star frame. Sorry, position of the star in the word frame, which is just something that we know. Position of the star in the word frame, and that's it. So this allows us to very conveniently compute the relative poses of things in relative frames of things. And yeah, so in order to truly understand it, we just need to work through a bunch of examples, numerical examples, and we will do this. But before we do this, let me just mention a bunch of like classical frames. So at least in my world, one very classical frame is so-called word frame, right? So word frame is basically wherever the word begins. So it's like a 0, 0, 0. It's just assumption that we make. So common place to place this 0, 0, 0 is like the base of the robot. So like home dock, like a docking station, something like this, right? Then in the word frame we might have like a bunch of keyframes. So as we have talked in the first part of the lecture and during the introduction, right? So those are very typically the frames that we periodically re-estimate, right? And then we locally measure the poses of the robot with respect to those frames, and then those frames are like measured. They are anchored to the word frame, right? They have their poses in the, so there's like position of keyframe 1, let's say, in the word frame. It's a typical thing we remember, right? So and how I'm drawing those, right, is like usually the z points up. This is kind of pretty typical thing to do, right? So another important frame is base link. So base link is basically like an arbitrary place in which the coordinate system of the robot starts. Very often, especially for diff drive robots, it's the middle of the axis. So the middle of the back axis. So yeah, diff drive robot is something like this. So for many different robots, it can be something different. Maybe for humanoid robot, right? Actually, I don't know if that's true for all companies, right? But like you could have middle of the head, that's possible, or center of mass. Center of mass is also very logical choice of this, and that's two possibilities, right? So base link, that's often how, or sometimes it's also called ego frame. And then quite often, right, like if you would have, for example, let's do like a bird's eye view of the robot. So here's like, and it has like 2 wheels, and then if the robot is intended to go here, here's like the sort of the front, then that would be the x direction, the first axis. This would be y-axis, and then pointing towards us would be the z-axis. This is quite usual. And then another thing is the camera and the image frame, right? And then I will make sure to come back to this and like be really careful about it. Like if you take an image, right? So especially a pixelated image, then it's conventional to count pixels. Oh no, and now I forgot. Wait a second. It's like 640, right, by 480. So this will be the X and this will be the Y, right? And then we begin counting from the top. So this goes as usual, but Y is flipped, has flipped orientation if compared to the usual situation, right? So it's like if you would have sort of yet another robot that is in the word frame. So this is the word frame, and maybe it points this direction, right? Then it sees an image, right? So maybe it sees an image like this, and here's like a projection, right? So through the corners, right? Then you would notice that the Z is kind of like minus Y in the image frame, and then I mean, of course, there's like rotation and so on. So like this relative pose needs to be expressed well, but like it's sort of like the X kind of goes into similar direction, and then Y is like Z. Like this, right? So this is image or camera frame. Image or camera. Yeah, so we have word frame, base link, ego frame, image frame, and camera frame. That's how it works, more or less. Right, and then let me have a look. Did I forget about something? Yeah. All right, so base link frame, right? So let me go back to the presentation. So in VSLAM we will have also like, okay, here's our robot again. Now it's looking more like this direction, right? So this is our base link. We will have sensor frame. So here's like one eye, and here's another eye, right? And then the camera left has some pose in base link. And then, yeah, based on these rules that we have explained above, we can smoothly transform between those. Yeah, and I think that's pretty much it. So maybe let me provide a bunch of references, and then I think we should practice those things actually in like a code lab or something. So very classic. Okay, so classic books that deal about this. So Intro to VSLAM. So there's a book, you could buy like a physical copy. There's also, they have an excellent website. So here it is. And yeah, you can pretty much just download it for free here, right? So the authors just provide it for free. Another, they have like a bunch of chapters about things. So there's like barefoot state estimation, another classic one. Yeah, also you could download this for free, completely legally, as far as I understand. And here's how the book looks like. And what else? Oh, if you are mildly interested in this like Lie theory, so just going deeper about the beauty of the mathematics behind this. So Lie theory, naive Lie theory. Here's the book, very nice book. My favorite book, which only touches on this, is this. It's not mainly about lead theory, but it has a bunch of chapters about this, and yeah, I just love this book. And yeah, so that's it for now, I think. Thank you for your attention. Hope it was useful.